Hi guys, welcome to my YouTube channel. Today I'm going to share a mathematical view of NRZ encoding decoding algorithm. Before we dive into today's presentation, let's answer the question I left in my last post on LinkedIn, which is with a 1 volt supply and assume a high Z input impedance for the second stage circuitry, has a differential swing of -1 volt to 1 volt handled by second stage circuitry. A high Z input impedance in the second stage circuitry means there's no impedance match for the output of the first stage circuitry. And therefore the output swing will be real to real. If the power supply is 1 volt, then the swing will be 0 volt to 1 volt for each of the P and N wires, right? The question, to answer the question, uh, I think the answer depends on the structure of the second stage circuitry. If the second stage circuitry continues to be differential circuitry, then the swing on each wire will be processed by the differential circuitry in second stage circuitry. Uh, so we don't need to worry about this at all. However, in reality, we usually do not use differential circuitry in the inner stages in op-amp or SerDes circuit. The reason is that for the input stage, when the receive signal, where the receive signal is usually very, very small, and it's very sensitive to the power noise and the common mode noise, right? Uh, which means we needed to have a very good PSRR, power supply reject ratio, whereas CMRR, common mode reject ratio, which can only be offered by differential circuitry. However, when the signal has been amplified pretty bit, and the output from the first stage, it is no longer so sensitive to the noise as the signal at the input of the first stage, right? And if we continue to use differential circuitry, we will need to double the silicon area, and which is very expensive. So that's the reason why we usually use single-ended circuitry for the inner stages in op-amp SerDes. So to answer that question, single-ended circuitry, of course, we cannot handle a swing as high as exceeding this power supply. The power supply is only 1 volt. The swing is 2 volt. No way to handle it. It will be saturated. And to prevent that kind of saturation, we have to use AGC, automatic gain control, whether to integrate it into the first stage or into the second stage. So that's the answer to the question. We need to use AGC in order to handle this over rail swing. Okay, let's go back to today's topic. You may ask, NRZ, it is the simplest code. It's just a bit 0, bit 1. What's the fancy in it? Well, if you look at its mathematical expression, it's actually not that straightforward. Here, um, we have the NRZ encoding equation, which is basically to calculate the NRZ wire signal. We have two wires, wire 0, wire 1, corresponding to N and P wires. And then we have Hadamard order 2 matrix. And then we have D in, which represents the input bit. And we have also have the dividing coefficient for 2, which represents the transmit termination effect. We want the signal output at the transmitter to be matched, right? The better matcher, the better signal. And with a perfect match, we will say the amplitude will be halved, which means if the power supply of the transmit is 1 volt, if we ignore the voltage drop inside the driver, inside the up arm and the lower arm, assume the voltage drop in both arms to be 0, then we have ideal output swing of 1 volt, right? Single-ended 1 volt. And with this termination, we not see 1 volt on the transmission line. We can only see half volt, which is 0 volt to half volt swing. Okay, what is this K? This K is a bit tricky. It represents the reduction ratio from dual supply, which is required by the antipodal encoding to single supply, and therefore it takes a value of half. That's where we first come across with antipodal, this word. I suppose it's quite new to folks here. We actually, why we have to use this antipodal value instead of, can we just use the original binary value here? Well, we can do the experiment. So if the input bit is 0, we put a 0 here. And the VCM, we can assume it to be 0 for a general case. And we do the math, 0, 0, and times or multiplies this 1, 1, and we got a 0, right? Which is the value of wire 0. And 0, 0, we multiply 1 minus 1, and we also got a 0. So we have both wires in 0 volt. Is that correct? When we are transmitting bit 0, both wire are 0 volt? No, of course not. It's not correct. And then if we put 1, bit 1 here, and then we do the calculation, we have 1 for W0, and we have minus 1 for wire 1. Well, that sounds reasonable. If we do this decoding at the receiver side, we will have 1 minus 1, which is 2. It sounds like reasonable, right? But the thing is, we cannot have half correctness, can we? We have to have 100% correctness. So bit 0, if it didn't work, that means this equation doesn't work. That's why the antipodal comes to play. So what is the antipodal? Antipodal means a point on opposite point on a circle or sphere um, to the original point. For example, we have original point A, then it's a typical point is right on the diametrical line, the opposite point. When it comes to binary typical mapping, we have original binary value 0. It maps to a typical value 1, and the binary value 1 maps to a typical value -1. As literally here, 0 is mapped to a typical value +1, and 1 maps a typical value -1. So, what's the physical significance of this atypical mapping? Well, it's actually the reason to use it is because it places the two binary symbol at the opposite extreme of the signal space. When we are transmitting signal, we want to fully utilize the available signal space, which is the swing range, right? And naturally, if we input a binary signal into the drive stage, we will see a typical signal presented at the output. For example, if we input 0 or 1 here, and we will say swing at here. If it's dual supply shown here, we will see a swing of +1 and -1, assuming both supply are 1 volt. And of course, ideally, we assume there's no voltage drop in this upper arm and the lower arm. And then we will see full real to real swing at the output. Despite the input is binary, the output will be real to real +1 volt to -1 volt. And of course, this circuit is a simplified circuit, and it cannot directly produce this +1 volt and -1 volt by itself, but with some, this is definitely doable, and this is quite, I would say, practically applied to convert binary input to plus or minus outputs. And if the VEE minus supply, negative supply, is actually 0 volt, so that means there's no negative supply, then the swing will be restricted to 0 volt to 1 volt. In other case, you might ask, well, does that violate this typical mapping? Actually not. If you put a capacitor here, and after capacitor, you will say the swing will be plus or minus some voltage. In that case, if this 1 volt supply, that will be plus or minus half volt with respect to the common mode voltage, right? So it's still atypical. And at the receiver side, if we have is an input signal that's present at the differential input, and at the output, we will naturally see the reverse atypical mapping. Differential input And we have a binary output here. And this current mirror circuit, which doubles the amplification of one side. It's also we will not lose the amplification when we convert the differential input to single-ended output. But actually, the current mirror doubling circuit doesn't change the nature of this reverse atypical mapping at the RX input stage. So this is why we need to use atypical, because it's naturally embedded in our circuit. At the transmit, it's a typical mapping. At the receiver, it's reverse typical mapping. Okay, once we have this atypical bit in the expression, then everything becomes normal, reasonable. For example, if the input bit is 1, which has a typical value of 1, then we put a 1 here, and we do the calculation, we will know we got a 1 divided by 2, divided by 2 again, and then we got a quarter volt via 0, and another a quarter volt via 1. You might ask, how come it's become only a quarter volt? Should it be a half volt, right? At the output of Y0? Well, it is a half as well, and depending on how you look at it. If you look at the output voltage of Y0, yes, it is 0 to a half with the 1 volt supply, and and that's the same for the Y1. It's just in the opposite phase, right? However, if you feed the signal through a capacitor, you will say at the capacitor side, it's plus or minus a quarter volt around the common mode voltage. So that's why we see a quarter volt here. And at the receiver side, if we use this voltage swing, we will get, well, actually same. Use either one, we get the same half volt. And half volt is scaled to 1 volt. Now let's change the input bit to 1 to verify if everything's still all right. We will have -1 here, right? It's a typical value. And we do the math. We will get -1 for on the top side, then divided by 4, we get negative quarter, and the positive quarter for Y1, and which corresponding to a swing of I think it's a mistake here. Sorry. It's actually plus half volt. And at the receiver side, we do the same decoding. Decoding is very simple. We just do a differentiation between the two wire signal. And we will get this minus half volt, which can be scaled to -1 volt. And applying the reverse and typical mapping, we will have the original binary bit 1 restored, right? So the whole mechanism kind of works well, and I guess that is the correct way of explaining and constructing this NRZ encoding decoding algorithm. If you have any comments, yeah, please do let me know. So the main takeaway of today is sharing is that NRZ encoding algorithm can be expressed using the Hadamard matrix, and with the input bit being its typical value instead of the binary value. And at the receiver side, the decoded signal needs to go through the reverse typical mapping to recover the original bit values. All right, that's all for today. Have a very nice day, and I'll see you next time. Thanks. Bye.